I'm going to share some project I've been doing recently. And while I prepared for this presentation, I found there's some related work, especially generative models. I will focus on introducing them and omit some details of my own work. Okay, the first slide is introduction. Why generative models matter? This is both because this way of AI is all about generation. Like ChatGPT, it can generate text. Midjourney can generate images. And what is generative models? From my perspective, I think the ultimate goal in generative modeling is sampling from realistic data distribution. So how can we sample from realistic data distribution? The most naive solution is that we can use a model to get a PG and use that PG to approximate PR. How can we approximate? Is that we can define a metric, we can define distance and minimize the PR and PG. And then as the PG has been approximated PR, we can sum from PG, the same as we can sum from PR. Nowadays, there is a more advanced solution. Like you do not approximate PR directly. You can use a score function to approximate the gradient of log likelihood. Actually, this is like a gradient descent. Using the gradient, you can use long-driven dynamics, and you can sum from PR. How can we approximate gradient of log likelihood is in this way. This is uh, uh, come from SDE, and using we have been approximate the log likelihood of gradient. We can sample, but and this is the noise diffusion probability model. But this method can be complicated. Let's go back.
Yes. Well, I got a question. What is X there?
What is X?
Yeah.
X means image or something you want to generate.
Okay. Okay. So you want this gradient to be 0, right? And as small as possible.
To be 0.
Or you are minimize it.
I want to approximate the gradient.
Okay.
And yeah, and this is exactly what diffusion model trying to do. But it is a little bit difficult. Let's go back to the most naive solution. We are using PG to approximate PR, and then we can sample from PG. And there is a key problem. We have to know what is a good distance. Usually, a good distance has three properties: non-negativity and identity. It means that distance have been non-negative. If distance negative, it can be strange. And if the distance is equal to 0, it means x is equal to y. And if x is equal to y, the distance must be 0. The second property is the distance between y and x. The second property is triangle equality. I will not cover too much about that in the later presentation. Let's take the property can be abstract. Let's take a Euclidean distance as example. Everybody is familiar with Euclidean distance. It looks like that. Actually, it certifies all of these properties. The first one is identity. If x equal to 1, then the distance is equal to 0. If the distance is equal to 0, then x is equal to 1. And the symmetry and the triangle inequality can be proved by Cauchy-Schwarz inequality, but we will not elaborate here. And this is a distance. This Euclidean distance can be mostly using in some other metrics like gradient, but it cannot be applied for probability distance metrics. Actually, the most commonly used distance is KL divergence. It is defined like that. And our traditional approach is that using the PG to approximate PR, use KR divergence. And this is the definition. We can split this term into two terms. And this term has nothing to do with PG. We can omit it. And minimize the negative log is equivalent to maximize the positive log. And if we can rewrite it in an expression form, we can use Monte Carlo method to estimate it. Actually, this is maximum likelihood estimation. We can get that using KI divergence. If we can make the model a bit more complicated, like if we can factorize PR into a sequence of elements using chain rule, then the MLE can be rewritten in this way. This is what we have derived from MLE. And using the chain rule, we can derive this term into a product and move it out from log. We can get the sum, right? And write in the expression form. What's this? Actually, this is autoregressive modeling. What's more, does K divergence is a good distance matrix? Let's look up if the K divergence satisfies all of the properties. The first property is non-negativity. And as we can see, as negative log is a convex function, we know convex function have good property. Like if we're using Jason's inequality, we can move the negative log outside and we get this term and it cancels out these two terms. We get this term and the integral of the probability is 1 and we can find that K divergence is non-negative. How about identity? If PG is equal to PR, it's easily to be proved that the distance is 0. So K divergence is a good distance matrix with regard to non-negativity and identity. How about symmetry? There is a very this is a problem. K divergence is not symmetric. When PR is greater than 0 and PG approaches 0, the integrand, as you can see, this term can go infinity. However, if PR approaches 0 and PG is greater than 0, as you can see, this term is 0 and the integrand goes to 0. It means that KL divergence is not symmetric. It inspires us to use a symmetric version of KL divergence. It is JS divergence. JS divergence definition is like that. Obviously, it is symmetric using commutative law. We can we can change the order, and we get it is symmetric. It is easy. Now we do not try to minimize the K divergence. We can minimize the JS divergence because it is symmetric. It is better. And this is the definition of JS divergence, and this is definition of K divergence. We can pull out the constant because it have nothing to do with x. And we can write it in this form, but we cannot get this term. There is a solution from GAN. It learns that. How can GAN learn that? It learns a discriminator trying to differentiate the realistic data and the generative data. And the optimal solution, if you can make some derivation, you can easily get that. The optimal discriminator looks like this. And you can substitute this term into here. We get this. And we can rewrite it in expectation form. And this term have nothing to do with generative model. We get loss from GAN. It leads to generative adversarial nets. While GANs is a good solution, there is an alternate approach. Instead of modeling the marginal distribution, we can model the joint distribution.
Mingyuan, one doubt.
Mhm.
Can you hear me?
Yeah.
Yeah. Like, why do you think that? Do you think that having some metric which is symmetric, the divergence which is a metric, is better than the metric which is like Kale divergence? Like Shannon is better compared to Kale divergence in terms of generative models. Is it better?
Actually, it is not a law, because we find some distance like Euclidean distance. It is naive and it satisfies three properties. And when we can imagine that any function satisfy the properties, it's a good distance.
No. In terms of generative modeling, do
Yeah,
you think that comparatively, I mean, instead of Kale divergence, if we go for J's junction Shannon divergence like GANs, it is better? Do you understand my question?
you mean YGS divergence is better than K divergence?
Kale divergence in terms of generative modeling. For my question is that you understood my question, right? I guess.
You mean Y symmetric distance is better than non-symmetric
Yeah,
distance?
For in terms of generative modeling.
Because from my perspective, it is this distance. Okay, what is distance? Uh, if okay, I think it may be a belief.
No. If you go to the if you go to the equation of KL divergence, which is probably let's use this one. Okay, maybe just use this one. Whichever you use. Okay, KL divergence.
Yeah,
Okay, so the equation I want to see the log p log thing. The previous slide,
log
maybe maybe the full equation of KL divergence.
or equation of
Yeah.
system.
Okay. Okay, you can just use this one. Okay. For example, if you look at the third line of the equation, right?
Okay.
You have, I mean, KL divergence equal to okay integral p log p over
Mhm.
p, right? I mean, this is not confusing. Can you just go to the original KL divergence definition, not the DJS, the DKL?
Original.
Yeah, I know that. I
Slide.
know this is correct, but it's difficult to
Previous
find.
slides.
Previous
Not
slide.
this.
No, previous slide. Because not everyone is familiar with it. Can you go to previous slide? Just show KL
Previous
divergence. Not
KL divergence.
okay.
Okay.
Okay, yeah, just this one. Okay. Next one. Next one. Next one.
This
Okay,
is
okay.
on.
Yeah. Okay. Okay. So if you let me see. KL divergence. Okay.
Actually,
You mean if this is the max actually a bit tricky, but like if you do minimum, it will be um um arc minimum PG over integral PX times
Sorry.
log,
I mean,
log
but this expression should contain log of PR by PG, right? Log of PR by PG. KL,
yeah, it's the original equation
yeah, so
is
that's why
PR by
I'm
PG.
asking you to show the
is
original
this.
equation. Yeah, that's
Yeah.
can I just put
Okay.
it, can I just stop here? The
Yeah.
reason is imagine, I mean because this equation the PG is in the denominator.
Yeah.
If that's 0, then the loss is huge.
Yeah. It's in.
If I mean, so if and if it's non-zero, for example, is big, then the loss is small. So this loss function, and when you are sampling, I think you are doing the PG, and when you are sampling, if I'm not wrong, your density will be sampled where PG is non-zero or big, while you
Yes.
are not doing, because there might be some places where PR is big, but there's no PG. you won't.
Yeah. I mean,
So
if it is not overlapping, PR and PG.
yeah, if they are not overlapping, so if PR has three
Yeah.
peaks, PG is only one of it, then your
Mhm.
model will sample crazily in the single peak of PG. No
Yes.
other peak of PR. So that is why asymmetry is bad in those distance equation.
Mhm.
Yeah. Okay. Then
So we
I
can say
continue.
that it can avoid that not mode collapsing problem, sampling from the same region if you use the KL divergence, right?
Yeah, it's true. Because if PR, because if you do some behavior like mode dropping, you can only cover some mode of PR.
Mhm.
You can okay.
Yeah. Only
Uh,
few samples of PR. Someone also, Rishi also shared. I think KL is bad because it's a mode seeking. Okay.
when actually, okay, where is it? Why it is a metric? That's the reason.
Yeah, that I know. Understood. Yeah. I mean, it just I was just thinking like why intuitively why Genshin Shannon is better than KL. Okay, no, understood.
Yeah.
We can
So
move on.
Mingyuan, I'm confused. Why in GAN you say it's actually estimate the symmetric distance, right? And
Yeah,
why? What's the disadvantage of using GAN?
Because you have to train in two stage. The first stage, you need to train a discriminator, and only when the discriminator converts, it's equivalent to this term.
Then why is bad?
It is too, it is you have to train another network. It is difficult to train
Okay.
actually,
I mean,
and they have some new papers talking about some new problem. Like there are some situations that PR and PG are disjoint. It is common. This is because PX is generated by a low dimension, generated by if the latent dimension is lower than X, then most of X that's density approach zero, and it means that the usually the density is disjoint. Okay, let me continue.
yes, of course.
Rather than GAN is a good solution, but there is an alternate approach is that we do not modeling the marginal distribution. We can model the joint distribution. We can introduce an extra variable called Z. Why it makes sense? This is because this is a sufficient condition. Why? If the joint distribution are equal, then the distribution must be equal, right? And that's sorry. Then let's focus on the KL divergence on the joint distribution. We can factorize the realistic joint distribution in this way because we can sample from PR, right? But we can only sample finite samples.
So
And
Z
we
here is latent.
PR
So
is what?
the Z here is latent.
Yeah,
Latent.
Z is latent. It's true. And we need an encoder to approximate the posterior distribution. And the prior distribution can be arbitrary. And given any z, we can sum from the z's, and we get the generator. We can factorize in this way. And using the definition of divergence,
Mingyuan, a simple notation doubt. Here you mentioned d of x comma z. Generally, it is dx dz, right? In notation, can we write in this way?
cannot be writing in this way. Okay.
I'm not sure. I was. Normally we should write dx and dz, right?
Easy.
So can we combine in this way? That I'm not sure. in the notations.
Okay, in this, actually, X has so many dimensions. Z has so many
Even X has
dimensions.
so many dimensions.
Yeah, because I do not need to make an integral on each dimension of X, and I do not need to, if I can like assume they are a concact vector, concact variable, I can write it this way. But maybe this is not standard, but you can understand that this law can be split in three terms, and this can be split in three terms, and the three term can be divided into three terms. The first is this. It is has nothing to all in all it is in three terms. Then this is KR divergence, this is decoder, and this have nothing to do with PG. And we get this loss. Actually, it's exactly the VAE loss. We usually do not get VAE loss in this way. We usually use try to maximize log likelihood under variational posterior distribution. This is what original VAE paper said. But we can get exactly the same loss using the KR divergence, use the distance matrix. Then I will focus on VAE. We use a very simple framework. We can derive autoregressive and GAN and VAE. I find it's beautiful mathematics, and but my work is about VAE. Then I will talk details about VAE. Let's look about the VAE loss or negative elbow. It consists of two terms. The first term is a KR divergence, and the second term is a reconstruction loss. Actually, the PZ can be arbitrary. The prior distribution can be arbitrary. So if we have different assumption on prior distribution, it can give different loss. Like in the original VAE paper, it's supposed PZ to be an isotropic Gaussian distribution. It's the most simple continuous distribution. And the posterior distribution looks like this. The non-diagonal elements tend to be zero. It means Z is conditional independent. But we may be wrong, but this way is original Way's assumption. And you want to calculate the KR divergence of these two terms. If posterior distribution is conditionally independent, then the KR divergence can be easily calculated. This is because you can factorize these two terms, and you can move the sigma out, and we have a sum, right? And we can move the sum out. We have so many integrals, and for each integrand, it have nothing to do with any other dimensions. So it means any other probability can be elemented when we get the marginal distribution. If we move it outside, and we get from marginal Gaussian distribution to
Mingyuan, in the previous slide, you mentioned it as posterior. It is posterior or variational posterior?
actually this is posterior.
But posterior, that's the thing for VA, right? You cannot have a posterior in a closed form, then you go for variational posterior. The terms are
Actually, we
different.
do not have a closed form of posterior, so
Yeah.
we're trying to approximate the posterior.
Yeah, that is called as variational posterior, because you are every time you are calling it as posterior, but we don't know what is the posterior, right?
Okay, we can call it variational posterior
Yeah.
distribution. Okay, and we can simplify the multi-dimensional Gaussian distribution to a single dimension Gaussian distribution, and looks like this. So we can only focus on each dimension. and it has a closed form solution looks like this. And we get the original where is loss. What's more, we can have different assumption, like in VQAE, it supposes that PZ to be a uniform categorical distribution, right? But how about posterior distribution, given encoder output? The solution is used in the original paper is with quantization. It given a code book with k cohorts, and the desacralization process is look like this. The code can minimize the quantization error is a selected code. So we get a posterior distribution. You look at that. If C is a code with
Mingyuan, go to previous slide. Like I want to understand the VQVAE. What's the motivation? Like here, PZ is categorical. So it's the latent is categorical.
yeah, the latence is categorical distribution.
So okay, like if there are, like if the length of the Z is n, only one Zi is one. Rest of them are zero, right?
Yeah,
Like
yeah,
hot encoder, one hot encoder. Okay.
yeah. One high encoder. You only
Okay.
because the nearest neighbor insertion is deterministic,
Okay.
and we
And one second. How can we get the posterior distribution given Z equal to, what does its statement mean?
we're
Expectation
trying
over,
to
in the
calculate
second line. Not this one, not this one. Here you are mentioned that how we, uh,
which
what C and no Z. Okay, how can we get the posterior distribution given Z equal to expectation of phi of X, right? What is this phi? Is this expectation?
oh actually phi is encoder, theta is decoder.
Phi is
Encoder.
okay, okay,
We get the latence from X, and
okay. So
we
you want
calculate
to, okay, okay. So you want to map some input point X to a one hot encoder, right?
yeah, it's true. This
Okay,
was
okay, sure, sure, sure.
yeah,
Next, so the solution is, so this is for unsupervised learning.
unsupervised learning. Yeah, it's true.
Unsupervised. Okay, okay, okay. Next,
Uh,
next to
yeah.
vector quantization, given a code book. What does this code book mean?
Code just like embedding, you have k dimension, k cohorts.
Like,
Each
where
each
does this
cohort,
code book?
yeah,
I mean, where does this code book come from? What does
mm,
it mean by given a code?
randomized, initialized, or something more complicated initialization strategy.
Like,
Just
what's the
tensor.
like what's the purpose of code book?
If you want to have a categorical latence,
Okay.
you have to do
Mhm.
something like this. You need to sample, you need to, because continuous, it is not continuous distribution, it is discrete
Yeah.
distribution. So
Okay.
you need to sample from this. It is categorical. It is discrete. Discrete.
Discrete.
Yeah,
Discrete.
yeah.
So this is also same dimension as Z.
Same. Yeah, it's true. Same dimension of
Okay.
Z.
Okay, but okay. Next, discrete can be expressed as. So
Yeah,
you here you are learning C.
yeah.
For every Z
How to learn
you are
Z,
finding.
I will show you later.
Okay, 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 fine. The code word C
But
is a vector selected from.
actually, I will not cover too many details about how to train Z about gradient explanation.
Yeah, that's fine, that's fine. But I just want to get what's the purpose of C, what is happening actually.
What
Okay,
happened
actually choose a code that minimizes the quantization
if
error.
we do not make the quantization, we just feed the Z into the decoder, we get an image. It is equivalent to autoencoder. However, in VAE or VQVAE, we have some constraints on latence. Like in the VAE, we have isotropic Gaussian prior distribution on Z. And in this situation, our prior distribution is category distribution, so we add some bonnet on it. However, when this quantize, we have some error, we have some quantization error, which never happen in autoencoder. We want to minimize it, and we will choose nearest neighbor.
So this codebook is sampled from a prior, which is multi-node distribution kind of thing.
It can be sampled, but
Some distribution.
now it is argmax. Argmin. I will introduce it can be a stochastic distribution, but nowadays as we are using a deterministic, there is a neighbor searching, so it is one hot distribution. And what is posterior distribution? It looks like this. Only the nearest neighbor have the probability is assigned to 1, and